Okay, so we're at the point where we have the acyl group activated with the coenzyme A in the matrix. This is where beta oxidation is happening. So you guys need to know what is needed to get out across the outer membrane and what's needed to get across the inner membrane, and why would this whole thing happen? Why can't you make it permeable to coenzyme A? Because then your acyl group would not be available for beta oxidation. So let's start discussing beta oxidation. This is only 4 reactions. It's just so lovely. We don't need to remember 8 or 10. This is only 4. And again, they're all enzyme catalyzed. And what they do is the whole purpose of beta oxidation is to chop our long chain fatty acid that's been activated with coenzyme A. It's to chop it into acetyl groups. So what we're going to do is we're going to chop between the alpha and beta carbon each time. So what we're going to be doing in beta oxidation is oxidizing the beta carbon. That's the whole purpose. In beta oxidation, we're going to be oxidizing the beta carbon. So we number, and if you've taken organic chemistry or even the last part of Gen Chem 2, you study organic chemistry. And you learn that an acid carbon is always numbered the first carbon. So this is carbon 1, 2, 3. So sometimes we don't want to use, it wouldn't be very pretty if we said third carbon oxidation. So we use Greek letters. Alpha is the one next to the carbon number 1. Beta is 2 away. So it's going to be third carbon oxidation or beta oxidation. So let's look at the 4 steps. How are we going to chop right here and make this activated with coenzyme A so it can happen again? Sometimes they call it a beta oxidation spiral because it keeps going until we're all done chopping up our fatty acid. So what we're doing first is we're going to put a double bond between the alpha and beta carbon. We're using FAD because that is the stronger oxidizing agent that is going to be able to put a double bond there. Is this some money? How many ATP can we get? 1.5. You guys know your stuff. All right. So we're going to oxidize that. Putting a double bond in is oxidation. Not just putting in a carbon-oxygen bond. Putting in a double bond, you're removing hydrogen. So that's an oxidation. Something else has to be reduced, and we get our money molecule. It's not a lot of money, but it's some. So that's where we're putting that in. Reaction 2. Oh, I can see what's going to happen. We're hydrating, right? And we're adding to a double bond. You put part of the water molecule on one carbon and the other part of the water molecule on the other carbon. So H2O, you have an OH and an H, right? And H2O. So the H is going to go on the alpha carbon and the OH is going to go on the beta carbon. Hydrate that double bond and put that OH. What do you think is going to happen next? You guys know. What's going to happen next? You have an OH here. Beta oxidation. Beta carbon. We're going to oxidize this OH to what? Yeah, to a carbonyl. So here we're going. Now we know that the oxidizing agent to put in a carbonyl to oxidize an alcohol is NAD. We're going to oxidize that to that. And so we get money. How many ATPs can we make from NADH? 2.5. So that's going to go on to the electron transport chain. So far, we've got 1.5 from the FAD, 2.5 from the NADH, right? Just by doing this oxidation. Then what do you think it's going to do next? Cleave it. And you guys knew this before it even happened. You could have gotten up here and taught this, right? So we're going to cleave that by taking another coenzyme A, and that coenzyme A, sulfur, is going to do a nucleophilic attack of the new carbonyl. That's going to push this or break this bond. And so now we have an acetyl-CoA. Where do you think that acetyl-CoA is going to go? It's already in the matrix. What pathway has an entry molecule of acetyl-CoA? Citric acid. So this is going to go on to citric acid and get our 3 NADHs and our 1 FADH2 and our 1 GTP, which is equivalent to ATP. Right?
Sorry, can you say that?
No, I'm just saying what I got out of.
No, but the beginning, what the sulfur.
The sulfur here.
Yeah.
All right, so you want me to repeat this?
Yeah,
the sulfur here, sulfur's, like it did before when we were doing our activation, sulfurs like to attack the carbonyl. Well, this one's already got sulfur on it. So this new coenzyme A is going to attack the carbon of a carbonyl. And that cleaving, or that attacking will cleave this bond because carbon only can have how many bonds? 4 bonds. So if the sulfur formed a bond here, then that would be 5 bonds, and that carbon would not be happy. So we're going to break this one because this will make a better leaving group for you organic chemists. And so here we get an acetyl-CoA that will go off. You can do like a little arrow. Citric acid cycle. Yes, Emmanuel. Sure. Want to go back to the last slide? Okay. All right. So this is going to go off the citric acid cycle. And now we have a new acyl-CoA. How is this different from our starting material from beta oxidation? It looks to me the same. It's got this red R, C double bond O. How is it different? It's going to be shorter by how many carbons? 2, right? Because we just got rid of these 2. This is the old beta carbon. So this new one, this product, is 2 carbons shorter than the starting acyl-CoA. What do you think we're going to do with this? So this is going off to the citric acid cycle. What are we doing with this? We're going to keep going. So we're cleaving that with that, and we're going to go, well, look at this. So you can imagine it keeps going until we have 4 carbons left, and then we do 1 cleavage. So let's look at this again. You have your fatty acid, and it's activated with our coenzyme A. We're going to put a double bond. You don't need to know any of these enzymes. We're not going to talk about control here. So we're going to put a double bond here. I need you to know that you're using an FAD for this. And we get some cash here, 1.5 ATPs. Then once we have that double bond, we're going to hydrate it. Remember? Malate or malate to fumarate to oxaloacetate. Or did I have that backwards? Yeah, all right. Malate has the OH. So, okay. So then succinate to fumarate to malate. I'm sorry, it's been. All right, I had it backwards. Don't take points off. All right. So, but look at what's happening here. It's the same thing, right? It's the same kind of idea where you want to have oxidation happen. How are we going to do that? You got to get a double bond in there that you can hydrate and then you can oxidize. Right? Same idea that we're having here. Double bond, hydrate it, oxidize that new alcohol, and then this is the new one. We're going to cleave it using another coenzyme A. So this is really the only new kind of reaction that we haven't seen before, where we're putting in a sulfur to attack the new carbonyl, and then that will cleave it. And then we have a fatty acid that's 2 carbons shorter, and there we go. So each cycle is going to give us an FADH2, an NADH, an acetyl-CoA, and right here, acetyl-CoA, and a fatty acid that's 2 carbons shorter. Yes, Emily?
You said that it keeps going through until 4 carbons are left, and then does it cleave again? Yeah. So it finishes when there's only... Yeah,
we're going to talk about that. So it keeps going until there's 4 carbons, and then we'll cleave there, but the last one gives you 2 acetyl-CoAs, so it doesn't keep going.
Can you repeat the products?
So the products of beta oxidation for each cycle, each spiral, is going to be an FADH2, an NADH, an acetyl-CoA, and a fatty acid 2 carbons shorter. Let's talk about how many times it's going to happen. I should have highlighted those while we were going through. Okay, so let's say we start out with 18 carbon fatty acid, steryl-CoA, activated with coenzyme A. Let's first talk about how many acetyl-CoAs are you going to end up with? What's this number here? 9. Okay, because if you have 18 carbons, you're going to get your 2 carbon acetyl-CoAs. So 18 divided by 2 is 9, right? But how many spirals, how many cycles are we going to go through? It says here only 8. But we get 9 acetyl-CoAs. Because that last time when you cleave, you get 2 acetyl-CoAs. So this is a trick that I'm going to test you on. Trick on the exam is that when you find out how many acetyl-CoAs you're going to get, you just take the number of carbons on your fatty acid and divide by 2. But when you find out how many cycles it's going to go through, you have to subtract 1 from that number because you end up with a 4-carbon product. So here you have your 18 carbons. We're going to cut here, so that's the first time. This is the second time. This is the third time, 4th time, 5th time, 6th time, 7th time, 8th time. Because that last time we have these 4 carbons, and when we cut, we get two acetyl-CoAs. Does that make sense to you guys? So you don't have to do a cutting. You don't have to go through the spiral because the last time you get a 2-carbon. So this is why most of our fatty acids are even numbers. Because then we go through beta oxidation. We don't have a 3-carbon that we don't know what to do with, right?
You say we're 18 carbon, but it's 7 cycles?
No, 8 cycles.
Or 8 cycles.
8 cycles because that last cycle, you get 2 acetyl-CoAs. So I need you to know, I give you a number, or say I give you 20. You know that you're going to get 10 acetyl-CoAs, but how many cycles? How many NADHs are you going to get? 9. FADH2s, 9. So you're going to know from that. Okay, let's move on to how much energy we get from, say, that stearic acid. So remember, we have it in our cytosol. We need to get it into the matrix. So this is just like we've done before. So the stearic acid, this is our 18 carbons. Bless you. We're going to take the 18 carbon, and we have to activate it. And remember to put that, to activate it, we go from ATP to AMP. So I'm going to say that it is investing 2 ATPs because it's losing 2 phosphates. So in my book, that's an investment of 2. Now, we make 8 cycles. We go through beta oxidation 8 times. So because it's 18 carbons, we get 9 acetyl-CoAs. So we're going to go through that 8 times. So each cycle we get 8 NADHs and 8 FADH2s. Then we have 9 acetyl-CoAs. Let's put that through the citric acid cycle. So this is through the citric acid cycle. Each time we go through the citric acid cycle, we get 3 NADHs and 1 FADH2 and 1 GTP. Do you want me to say that again? So here, let me back up. This is our beta oxidation. We know from each cycle of the beta oxidation, we got 1 NADH and 1 FADH2. Since we went through it 8 times to get the 9 acetyl-CoAs, we get 1 of each. So that's 8 total. We got 9 acetyl-CoAs from the 18 steryl-CoAs going through beta oxidation. Let's put those 9 through the citric acid cycle. So here, we should say citric acid cycle in your notes. And each time you go through the citric acid cycle, you're going to get 3 NADHs and 1 FADH2. You're also going to get a GTP. So let's take 9 times the numbers I just said. 9 times 3 is 27. 9 times 1 is 9. And 9 times 1 GTP is 9. Remember I said GTP can just transfer its phosphate to ATP. So we're going to count that as an ATP. Now, yes?
Quick question. But why would you not multiply it by 8 if you're going through the 8 cycles?
Remember when, if you're 18 carbons long, you're going to get 9 acetyl-CoAs.
Right.
So this is the 9 acetyl-CoAs that are going to enter the citric acid cycle. So that's why we're multiplying it by 9, because we're going through the citric acid cycle with each acetyl-CoA.
Oh, okay.
We're only multiplying this by 8. We're only going through beta oxidation 8 times.
Okay.
But we're going through the citric acid cycle
To use
9.
Up all
use up all the acetyl-CoAs. Thank you for asking that. Now what we're going to do is turn these in. For every NADH, we're going to get 2.5 ATPs. So 8 from the beta oxidation gives me 20. 2.5 times 8 is 20. The 27 is going to also give me 2.5. So 27 times 2.5 is 67.5. FAD doesn't give us as much. It's only 1.5, so let's turn in this 8. We get the 12, the 9, we get 13. So we net for our 18 carbon fatty acid, we net 120 ATPs. That's a lot. All right, now we compared it. How many did we get from a glucose? 30 to 32. 30 to 32, depending on the shuttle. So, but that's not really a fair comparison, is it? Because how many carbons is glucose? 6. And this one is 18. So what we're going to do is multiply. Let's use 3 glucoses so that the number of carbons are the same. So, and let's use, the higher number so we have a fair comparison. So 3 times 32 is 96 ATPs. So we get more energy out of our fats than we do for our glucose. So you want to have more energy, you should eat more fats. That didn't really help me with my run this morning.
I just want to verify, so 18 carbons, it's 8 cycles, and you get 9 acetyl-CoAs.
That's right.
And then this 9 acetyl-CoAs go into the citric acid.
That's right. So 18 carbons gives you 8 beta oxidation cycles and 9 acetyl-CoAs. I know it can trip you up a little bit. That's why I'm saying that it's you gotta. That's something you're going to have to stick in your head because it can throw you for a loop. And then we all know what you get out of the citric acid cycle. I like this comparison because we're doing a carbon for carbon comparison. 3 glucose molecules compared to 1 fatty acid that's 18 carbons long. So we're carbon for carbon. So, and why is this? Glucose is already oxidized, right? Remember, we had to do all this work right here. This work was to get it to be oxidized, right? So we got some This is where we're getting our extra money from. Beta oxidation is where we're getting our extra money from our fatty acids. What do we do with odd numbers? I don't expect you to remember pretty much anything from this other than when you have an odd number fatty acid, we don't just throw it away. Okay? What we do is we do a number of things. So if we end up with an odd number, or if we start with an odd number fatty acid, then at that last cleavage, we're going to end up with a 3-carbon instead of a 2-carbon acetyl-CoA. We're going to end up with propional-CoA instead of acetyl-CoA. What do we do with this oddball 3-carbon? We can't put it to the citric acid cycle. Acetyl-CoA is the entry molecule, not 3 carbons. So what do we do with it? Well, we can rearrange it to make succinyl-CoA. We can do a number of reactions, and that will rearrange it, and then we can feed in to succinyl-CoA. Just remember, we're not going to waste anything, right? If it's a carbon, we're not going to waste it. So it can just feed into the citric acid cycle.
Is that what we were talking about with the fatty acids and proteins and stuff that can be broken down and added in as intermediates?
Yeah, that's right. So this is exactly what we were talking about when we can feed into the citric acid cycle or siphon off. So feeding in and siphoning off. So feeding in is catabolic, siphoning off is anabolic. So this is exactly what we were talking about, an example, where we're not going to waste it.
So anything that can't directly go into the cycle as a product will be broken down or built up to be added in?
Yeah, it can be. It can be, not always. It might be taken off to do something totally different. There's a lot of different pathways out there. It's not going to definitely go into the citric acid cycle, but that's one thing that can happen. That's why the citric acid cycle is called the central metabolic pathway, because pretty much everything can be fed in, and everything can be made from things being drawn out from it. I don't know all those pathways. I don't know every biochemical pathway. In fact, I know very few, but this course is meant to be a guide for you as you meet new pathways. Just like we saw with the parallel between the citric acid cycle, that I got wrong, and the reactions that were in beta oxidation. Okay, we wanted to get a carbonyl somewhere. What did we do? We put a double bond, hydrated it, and then oxidized it. So that's what the cell does. How about unsaturated fatty acids? They're all, and this I have trouble with this, and I have yet to reconcile myself with this process. Unsaturated fatty acids, natural ones are going to have what conformation, a cis or a trans? Cis, right? Man-made is trans. So all unsaturated fatty acids are cis. But what does the body do? It isomerizes it to a trans. And then it goes on. So why are trans fats bad for you? See, I don't know. I have to figure that out. I've yet to learn that. So if someone finds out in their future, please email me. Because I don't know what, I guess maybe the body doesn't know what to do with being presented that. I don't know.
If it's now a trans fat, is it?
Let's look. So I don't really know. So this is what's going to happen. So here, I know this is really tiny. I don't know what to do to make it better for you guys. Do you see any of this back there? All right. I'm not going to ask you to remember too much from this, but here we have a fatty acid with a couple double bonds in it. So here we have 6 carbons, so 7, 8. So we don't get a double bond until 9 and then 12. So we're going through our beta oxidation. We do it 3 times, and then we're stuck. Oh, what do we do here? So we want to put a double bond here, right? But that's not going to happen. So what we do is we take this and we make it a trans, and then we do beta oxidation. So it isomerizes it from here to over here, and it makes it a trans. So enol-CoA isomerase will make a cis double bond between the beta and I guess the gamma carbon, a trans between alpha and beta.
So when it isomerizes,
it moves it over.
It completely moves.
It moves it. It moves the position and then makes it a trans. Yeah, this is a pretty powerful isomerase, right? And then it goes through. So it's happy. We've actually gained some, work. We didn't have to use the FADH or FAD to do this. So you're not getting that money out. You're losing money by having an unsaturated fat. Because remember that oxidation to put that double bond in, you got an FADH2 out. That was 1.5 ATPs. We're not getting that money here. Not happening. And so then we go through, we get our acetyl-CoA, we do it, and then we have to do it again. We use another, this is all I want you to know from it, that you have to go from a cis double bond to a trans double bond, and that you're not going to get the FADH2 out of it. Oops. We're not going to get the FADH2 out of it.